It sticks on. That's crazy. That's crazy. That's crazy, boy. Holy shit. I think they are charging. What do they do? What do they do? Oh my God. Do not charge me. Why are you charging so much? What do you mean? I freaking lost time. I had to. There's only.
Okay, are we ready to talk about this one? Ready. Okay. All right. So we have the first one is manganese 4 B. What would the cation be? And then 4+. Good. Remember when you put the charge in, you have to put the number first and then the symbol. So 4+. Okay. Good. And what would the anion be? Br minus, perfect. Br is always going to be minus. So that's how we can figure out the Mn. We have 4 minus charges, so Mn must be 4+. Good. How about here? What would the copper charge be? Cu2+. Good. Iodine. Good. Yes. This one is chromium. What would the charge be on chromium? 3+. Good. And then fluorine. Good. Cobalt. What would the charge be here?
Plus CO+.
Those ones?
Oh, it's
yeah.
These two cancel each other sometimes.
Yes. So yeah, we have to look at the oxygen. What's the charge on oxygen? 2 minus. So it's O2 minus. So that tells us copper or excuse me, cobalt. Good. Okay. Do you think you could do something like this on the final? Okay. So that's going to be something like the final. Okay. Let me pull up my camera so that if people miss, they can have this. So, remind me, so last time we made sure that we measured our copper, is that right? Okay. Is there anyone else who needed to measure the mass of the copper in the nail? That's from last time. Oh, you need to measure? Okay, so go ahead and Corbin's also next. So grab some tissue glasses and measure the mass of your nails and your copper. Okay, so you should have been able to fill out all of the data tables now. So this table and this table. This table needs a little bit of math. So let's talk about this table. Let's see. Were we able to get all of the information in this table okay? So like mass of nails after the reaction, that should be just the dry nails. You should measure those, the mass. Mass of the beaker plus the copper should go here. And then you can figure out how much copper you have, mass of the copper produced, by taking the mass of the beaker and the copper and subtracting off the beaker, and that should be your copper mass. Do you agree with that? So if you haven't done that already, figure out the mass of your copper produced. So you're going to subtract the beaker off of the mass of the beaker and the copper. Okay, what are some values that you got? How much copper did you get? You get like 10 grams, half a gram, 6 grams, 6.52 grams. Okay, so on the order, and you all did different experiments, so you're all going to have different values. But let's go ahead and use that. And I like how you have 3 significant digits for that because you use a scale that has 2 decimal places. So you're saying you had 6.52, is that right? Grams. So we'll use your value of copper produced. Okay. So the question down here says how many moles of copper? How are we going to find moles from grams? What do we need to do? Perfect. Divide by the molar mass. So we can look at our periodic table, and copper is 63.5, I think. We'll just use 63.5. And this is grams per mole. If we're dividing by grams per mole, our value will be in moles. Okay, you should be doing this with your value, not Nicole's value, your value. So how much copper did you get? Okay. Did you get half a gram? Did you get 12 grams? How much copper did you get? Okay, here's my calculator. So take your mass divided by the molar mass of the copper, and that will give you your moles of copper. Okay, how do you find the mass of the iron? Used. This is not iron used in the reaction. What's that? So you started with a massive nail, the mass of your nail, massive nail before reaction. Then you have the mass of the nail after the reaction. We're going to assume that everything that came out of the nail is the iron that we used. Okay, that's our assumption here. So mass of nail before minus mass of nail after, that gives us the mass of the iron used. So what on the order of how much copper, or excuse me, iron, how many grams of iron did you have? 2 grams? Okay, we're doing okay? Questions? I don't feel like we're together. Are we together? We're okay? Did you find the mass of the iron you used? Okay. Okay, so mass of the iron you used, let's make up a number. I don't know. How many mass of iron did you use?
1.12.
Okay, so 1.12 grams of iron. So you should use your number, not this number. So find the moles of iron. Again, find the molar mass of iron. I think it says 55.
Yeah,
845, and that's always grams per mole. So remember, if we have grams divided by grams per mole, that ends up being like this. Oops. And then grams cancels, we'll end up with moles. So grams divided by molar mass gives us moles. Okay, so that's how you're going to find this box. So mass of iron you used divided by molar mass gives you the moles of iron. Okay, questions so far? We're doing okay? Okay, next question says moles of copper per moles of iron, and that's a decimal. So you're going to take the first box that you just found divided by the second box that you found. I don't know why this is not on the same page. So moles of copper is the very bottom box on the first page. Moles of iron is this box. So moles of copper divided by moles of iron, and put that as a decimal. How many sig figs should we have? Good. Our other numbers had 3, so this one should have 3. Good. Okay, this one's different. This one's like that number upside down. Moles of copper divided by moles of iron, and we're going to round it to the closest whole number. So I only want to see one digit here. Okay. So if I get, for example, I'm just going to make up a number. If I got like 6.73 as my number here, I'm going to round to the nearest whole number, which would be 7. Okay. I want only a whole number. If I got 0.5, I'm going to round to 1. That's my nearest whole number. If I got 2.3, I'm going to round to just 2. Okay. So this value, you're going to flip it. Moles of copper. Oh, it's the same number. Why did I think of flip it? Don't flip it. Sorry, my bad. Moles of copper divided by moles of iron. This is your decimal. Take this number and truncate it. So closest, no. This one you do not keep sig figs. I want the nearest whole number. It's a ratio, so it doesn't have a unit. Because moles over moles. No unit. Good to check that. Okay, that's my bad. I thought for some reason it flipped it. So you don't flip it. Moles of copper over moles of iron, so it's the same number, you just truncate it. Round it to the nearest whole number. Get rid of the decimals.
So that means on copper.
Does anyone want us to do your example up here? We got it?
How do we label them like that?
Oh, yes. Let's see. So this one and this one are ratios. So we don't have units. No units. Just leave it. This box is telling me what it is. Does that make sense? Yeah, so no units. This one should have sig figs. This one should not have sig figs. You're just one number. This one's just this number rounded to the whole number. Clearest, nearest whole number. Okay, we're doing okay so far? Okay. All right. We'll do some of these. Okay, so let's think about this. So we have a beaker. And in our beaker, we had a nail. We had 3 nails. I'm going to draw 1 nail. Okay, this is my nail. And in our nail, we had iron. Okay, so iron is a solid. Okay, what was in our solution? Do you remember what you added? Yes, good. This is copper chloride. Okay, we just talked about this topic. So what happens to copper chloride in solution? This one's ionic. We have a metal and a nonmetal. So what will we be looking for?
It's soluble.
If it's soluble, so this is soluble, we dissolved it. So remember, what will this break into? It's ionic, so it's going to split into its ions. So this one's going to be copper 2 plus ions. This is going to be chlorine minus ions. So we've got, instead of this chunk of solid floating around, so this is our nail, we have copper 2 plus floating around, and we have chlorine minus floating around. Okay? All right, so what's happening, and think back to chapter, I think it was chapter 5, where we had iron, which is a solid, something like this. And then we add something that's soluble. This is not balanced yet. What did we end up with? So think into the lab. What did you measure second? What is the precipitate that formed today? Or not today, for this lab? Yeah, copper. So we have copper solid. And we also end up with iron chloride. Okay. Iron is going to be, this is what we're trying to figure out. We're trying to figure out this ratio. Okay. We don't know how many irons to chlorines yet. Do you remember what this reaction was called from chapter, I think it was chapter 5, the very last topic? Do you remember? This one's called an oxidation reduction reaction. Do you remember that from chapter 5? Kind of? Good. Okay. This is also known as, so you can put this is also known as a replacement reaction. Okay, so either of those are correct. In our instructions, it tells us it is a replacement reaction. But if you think back to chapter, I'm pretty sure it's chapter 5. Remember we had to figure out which one's going to be a solid. Do you remember doing that? Okay. Well, maybe we'll review that one also. Okay, so what is happening to the iron atoms and copper during the reaction? So based on what we just talked about, what is happening to the copper? Or we can look at our reaction. The copper is opposite. Copper is getting reduced, becoming a solid. So either of those is true. It's becoming reduced, it's becoming a solid. The iron is being oxidized. The iron is dissolving into solution. Okay. All right. So then we have to think about, let's go back to question 1. Let's make sure we're on the same page. So what happened to our reaction? Why did your reaction stop? Yeah, Eve.
Because once like the magnesium is fully dissolved, then it already dissolving.
Okay, and we were talking about the nail lab, so do you mean the
Sorry.
iron?
Yes.
Okay, so the reaction stops. So think about in your beaker, you started with copper chloride as a blue solution. At the end, did you still have a blue solution? So what reactant got used up? The liquid, which was the copper, right? Did you have iron? Did you have nails to measure at the end? So did the iron all get used up? No. So in this reaction, the copper got used up.
So it's the reactant, right?
Yes. Which reactant was used up? Copper chloride. Good. So that's what it's talking about here. What happens to the ratio of copper to iron if you place more nails in the beaker? So would you produce more copper if you had more nails?
You would use it.
Yeah. You wouldn't have, because you already have nails left over, right? Yeah. You would need more copper, right? So our ratio wouldn't change if we use more nails. What happens if we stop the reaction really fast? So we started it, we only let it run for like 5 minutes, and then we stopped it. What would happen to the ratio? It didn't finish, so that tells us that we would have less moles of copper to iron. So that means we would have a smaller ratio because we would have less copper produced. Okay, number 4. What is the accepted ratio of copper iron atoms? Let's see. Yeah. What is the accepted ratio? So let's first do number 5. I feel like this will make more sense if we do number 5 first. So the first thing that we need to do is balance the equation, and then we'll think about the accepted ratio. So we talked about we have iron, which is a solid. We added it to copper chloride. I don't know why I'm putting parentheses. I don't need parentheses. And then this goes to copper, which is a solid. Okay. Plus, this is what we're looking for. Iron chloride. Okay, we're trying to figure out the ratio. We don't quite know this. Are we supposed to look this up? Count for differences and the accepted value. Am I supposed to give you the accepted value? Let me see in the teacher instruction. Also, let me see this.
Basically, this one, since they didn't change, if we let it go, so the ratio would change. If you let it go, if you add much.
Oh yeah, that's so sad. Okay. Okay. So our accepted rate value, let's go back to this one for a minute. So the accepted value is 1 to 1. So then you need to look out, so write that down. Number 4, the accepted value is a 1 to 1 ratio. 1 copper atom per 1 iron atom. So let's go to here. What is your ratio? Is yours a 1 to 1? Is yours a 2 to 1? So compare to the accepted value. And it doesn't have to be the accepted value. Ours is an experiment and the other one's like theory. Okay, so what could have happened to make your value different than the accepted value? Any ideas? So did everyone get a 1 to 1 ratio? Did everyone get 1 in this box? Oh, we got a 1. Nice. Is there anyone? You didn't get 1. What did you get?
I got 1.
Oh, you got 1. Oh, you just raised your hand.
We had 3.
You had 3. Okay, so you have 3 to 1. So what could be the reason that you're getting more copper than iron than you should? Does that make sense? That's a question you have to answer, and lots of reasons. So for example, if you don't think your sample was dry, then you're getting too much mass in your copper. If you think you lost some mass of your nail somewhere, like maybe some people's nails were like breaking, maybe some of the iron was actually in your copper mass. Does that make sense? Maybe you lost a piece of your nail. That could account for that. Okay. Maybe the copper had a lot of impurities. That would make your mass larger. Okay, there's lots of reasons for that. Just you need to think about what could have happened. If yours matched pretty well, then you're good. Okay, so now we need to go to our balance equation. Oh, I still need to know. Let me see if they tell me how we're supposed to know what the ion charge is. Okay, they don't really tell us. Okay, we're just gonna assume. So I guess because copper is 2+, maybe we're gonna assume that iron is also 2+. I'm not sure that's acceptable, but that's what we're gonna do. So if iron is 2+, then this is chlorine. Chlorine is 2. Okay, is this balanced? Yeah, balanced. 1 copper, 2 chlorines, 2 chlorines, 1 iron, 1 iron. And this is where we're getting it's 1 iron for 1 copper, 1-to-1 ratio. Okay, you don't have to write the coefficient. I'm just showing you that coefficient. Okay, write the balance equation. Questions for me so far? Okay. All right, so I think that is the first part. Okay, the next part is the balloon lab. We need to do some calculations. Is this worth your time to do the calculations? Okay, just making sure. I know that if you all did it, then let's not do that, but let's make sure we understand this. Okay, so number 1 on the balloon lab. So remind your neighbor, what did we do in the balloon lab? Tell your neighbor for a minute. Remember, what were we doing? Oh, yeah, go ahead and go. All right, so we did something like this. I am going to draw a balloon. This is my balloon on my Erlenmeyer flask. And then this balloon got a little bit bigger. And this balloon got even bigger. And then this one kind of didn't get bigger. Do you agree with that? My rough picture? So this one we had to put about 0.07 grams, 0.15 grams of magnesium, 0.30, 0.60, about, right? Does that sound familiar? And we put the same volume of 3 molar hydrochloric acid in each of these. It was 10 milliliters. Okay. All right, so the first question says, perform stoichiometric calculations to show why the volume of the balloon with 0.15 grams was about 2 times the volume of the balloon with 0.3. I think they switched that, so yeah. This one was about 2 times the volume of this one. And we're just trying to show that. Okay. So we have a mass, and you should use the values that you measured out. If you measured exactly 0.15 grams, use that. If you use 0.12 grams, use that. Okay, so I'm going to use these values because those are the values in the lab, but you should use your values. Okay, so what we need to do is figure out how much, oops, that's mg, how much magnesium, or not magnesium, how much hydrogen gas did we produce from the magnesium that we used. So I'm going to put 0.15 grams And I need to convert that to moles. So how many moles of magnesium? So we just talked about this. We got to divide by the molar mass of magnesium, which is, I think it's 24. I can't see that far. Let me pull out this periodic table. 24.305 grams per mole. So I'm dividing by the molar mass. That'll give me moles of magnesium. Okay. And again, you are using your values, not the given value, unless that's exactly what you measured out. That's not expected. Okay. And I have 2 sig figs, so I'm going to keep 2 sig figs, 3.6 moles of magnesium. Okay. And then I need to relate this to moles of hydrogen. So we need to write a balanced equation for if we have magnesium and we add hydrogen, or we add hydrochloric acid, we're going to produce hydrogen gas. That's what we're trying to relate. How many moles of hydrogen for how many moles of magnesium? And what else do we produce? We produce magnesium chloride. Okay, magnesium always forms a 2+ charge, so I'm going to need 2 chlorines. Okay, so then we have to balance this. It looks like I need to put a 2 in front of the hydrochloric acid. So then we have 1 magnesium, 1 magnesium, 2 chlorines, 2 chlorines, 2 hydrogens, 2 hydrogens. So now it's balanced. Okay. So this is showing me that for every 1 mole of magnesium, I should get out 1 mole of hydrogen. Do you see that? So this is like 1-to-1 ratio, magnesium to hydrogen. So it's like 1 mole of magnesium gives me 1 mole of hydrogen. And then we'll have 3.6 moles of hydrogen. So if we start with 0.15 grams of magnesium, we should end up with 3.6 moles of hydrogen. Okay, so that's our first comparison. We're comparing, if we start with 0.15, we'll get 3 moles, excuse me, 3.6 moles of hydrogen. Okay, question so far. You see where we're going? Oh, thank you. I did multiply them. Thank you. Okay, very good. Thank you for catching that. So now that I've divided them, I got 0.06. I'm around to 2 decimal places because this one has 2. 2 moles of magnesium, which is the same as 0.0062 moles of hydrogen. If I start with 1 mole of magnesium, I should get out 1 mole of hydrogen. Okay, so then we're going to do the same thing, but we're going to compare, well, how much do we get out if we start with double, or whatever you did for the third experiment? Is that 5? Okay, so same thing, but with...
Wait, on that one right there, is hydrogen supposed to be on top or magnesium?
Oh, this is my answers.
Oh.
These are just my 2 answers.
Oh, okay.
I erased the conversion. Hydrogen should be on the top in your conversion. Okay, so 0.012 moles of magnesium, but we decided it's a 1-to-1 ratio. So for 1 mole of magnesium, I should get out 1 mole of hydrogen. So this translates to mole of hydrogen.
Is this for the second one?
Yes. So if we start with, well, it's for the third experiment, the second part of our calculation. We're comparing 0.15 grams to 0.13.
Is that 24?
Yeah, this is the molar mass. Molar mass of magnesium.
Let's say 24.03.
Yeah, 24.305. My pen is not very Okay, so what do we notice between this number and this number, or your numbers? What are you seeing? If you double the magnesium, what happens to the moles of hydrogen? Also doubles, great. And that's what you're trying to show. Even though this question is worded incorrectly, you should get out double the hydrogen with double the magnesium. And that's what we are seeing for from 3 to 4. Yes?
So basically, the reason it's bigger is because
So the first part, you should have seen from so this is like 1, 2, 3. From 2 to 3, this should have doubled. From 3 to 4, did it double? This didn't double. Okay, but we're looking right here, 2 to 3, from 0.15 to 0.3, that doubled. So we're just trying to show why it doubled. Well, if we doubled the hydrogen, then we double the magnesium, we double the hydrogen.
why did it not double from 3 to 4?
Yes, that is the next question. So we have to look at how much hydrochloric acid there is. Are we okay on the first question? Yes. Yes, the answer is calculations. Show me.
So you don't have to write it in words at all?
No. Show me that if you double the magnesium, you double the hydrogen for those two. You should use your own values, not what's in the problem or like in the instructions. Whatever you measured. Okay, next one. Perform stoichiometric calculations to show why the balloons with 0.3 grams and 0.6 grams, so we're comparing the two last balloons, why did they inflate to approximately the same size? So this one we have to account for the limiting reactant. So we have to figure out which one's limiting. Are we okay on this whiteboard? Can I erase this whiteboard? Okay. All right. So let's erase that. I'm going to erase this, so kind of think about what's happening. I just need more space. Okay, so we still have, let's use our equation. We have HCl, we added magnesium, we needed 2 of those. We went to hydrogen gas and magnesium chloride. Okay, this is chlorine. Okay, so we're going to do the same thing, but we need to figure out how much hydrochloric acid did we use each time. How much HCl? So we know we had 3 molar hydrochloric acid, and we know that we used 10 milliliters of that. Okay. I can't remember. Have we briefly talked about molarity? Have we talked about this, Big M? Have we got there yet? Okay, we have. Okay, so this is moles per liter. Does that sound familiar? Okay, so we have 10 milliliters of 3 molar. So what we're going to do is we're going to take molarity times volume, and that will give us the number of moles. But our units have to match. So this is moles per liter. This one's in milliliters. So I'm going to move the decimal 1, 2, 3 to get liters. So I'm going to take 3 molar. This is moles per liter. 3 molar multiply by number of liters. So liters cancels out. And that will tell me how many moles. Of hydrochloric acid. So we used 0.03 moles of HCl. Okay, so we need to know that to compare. Yes. That was what was labeled on the bottle, and that's also in the instructions. It tells you what concentration to use, and that's where that's coming from. So yeah, if you accidentally use the 1 molar, then you would use the 1. But
on the end of it, H.
Moles of HCl. Oh, good question. We ran out of space. 3.03 moles of HCl. Okay, we already figured out, maybe you'll have to remind me. So we are comparing 0.3 grams of magnesium to, we're comparing that to, let me scoot this back a little bit. We're comparing that to 0.6 grams of magnesium. Which one is limiting in each case? So this was like number 3, the bottle, and this was like number 4, the experiment. So we already figured out if we use 0.3 grams, we divide it by the molar mass. Oops, 305. That was that 0.0062 moles, okay, of magnesium. Okay, so we're going to do the same thing. How many moles of magnesium if we start with 0.6 or whatever you actually measured? So, do that should also double. Oh, this one wasn't 0.62. This one was 1,2, right?
Yeah.
Thank you. 1,2. So this one's 0.6 divided by 24.305. So 24, and that makes sense, it's doubling. Let me round to 2 decimal places. These had 2 decimal places. Sorry?
So ours going to be a little off.
Yes, yours will be different because you use different values. The process is the same. The trends are the same. Yeah. Okay, so from this, we need to look at our equation. If we use 1 mole, let's see, if we use 0.012 moles of magnesium, how much hydrochloric acid do we need? How many moles to use up all of the magnesium? We just need double that, right? So, or we could set it up. For 1 mole of magnesium, we need 2 moles of hydrochloric acid. So I'm just using my chemical equation. This is a 1-to-2 ratio. So I would need 0.024 moles of HCl. How much HCl was there? Well, every time we had 0.03 moles of HCl. Are we following okay? Okay. So how about this one? Need. If we start with 0.025 moles of magnesium, how much, to use all of this magnesium, how much hydrochloric acid would we need based on our ratio, 1-to-2? Yes, 0.5 moles of HCl. And how much did we have? We only had 0.03 moles. Like, oh, I need a 0 here, sorry. Can't fit it. 0.05, there we go. And we only had 0.03 moles of hydrochloric acid. So we have So that tells us about the limiting reactant. So for number 3, or reaction number 3, what was the limiting reactant? What ran out first? So we had 0.012 moles of magnesium. And to use all of this up, we would need 0.024 moles of hydrochloric acid. We had a lot of that. We had more, right? So this one is, in this reaction, magnesium is limiting. But in this one, what's happening? Well, we added way more magnesium. We doubled our magnesium. Now we need 0.05 moles of hydrochloric acid. We only have 0.03. So all of the magnesium gets used up. Or not all of the hydrochloric acid gets used up. And hydrochloric acid is the limiting. And so then we stop the reaction. We can't make any more hydrogen gas. Okay, so number 2 is you're just answering the question using your math, showing your calculations, relating moles to moles. Question 3. How did the volumes of hydrogen gas produced as measured by the size of the balloons? You didn't have to measure the balloons, just visually. You should be able to see. They stopped doubling in size. Did that match what your results were? And also think back to your pre-lab. You were supposed to predict something based on the value, the mass of magnesium added and hydrogen produced. So think back to your pre-lab. Did your results match your prediction? Okay. And then number 4 and 5 is asking, so magnesium is limiting or hydrochloric acid is limiting based on if we use 0.3 or 0.6 grams of magnesium. Okay, questions on that? Do we follow along okay? Okay. Questions before we leave? All right. Okay, let me pull up my Alex while you finish that up.
So,
Okay, my Alex logged out, so give me a minute. Because we did the lab in class, we have about half an hour of class. We're going to try to get through topics. We'll probably just go to the class. We'll talk about it.
the biggest what was related, hypothesis correctly said on that as an object bigger cylinder reaction. So more magnesium, more hydrogen produced. Yeah.
Okay. Here we go. So this is chapter 8. We're going through the topics. Here is my list of topics that we need to get through. So last time, did we talk about light dissolves light? We talked about hydrogen bonding or ionic dissolves in polar. Okay. So this is the next question that we need to go over. Understanding how solubility varies with temperature and pressure. This one is a reasoning question. Okay, so let's write down a few rules that we're going to use, and then we'll do the question. Okay, so some of these are intuitive, they make sense, and some of them are less intuitive. We have used gas less often usually. Okay, so if we have a solid dissolved in a liquid. So imagine yourself, you're making syrup and you're putting sugar in water. So what can we do to affect the solubility of the sugar? Heat it. Okay, so if we increase the temperature of a solid dissolved in a liquid, what will happen to the solubility? So if we increase the temperature, we probably are familiar that the solubility will increase. Does that sound familiar? Okay, great. Let's see. So that means what happens if we decrease the temperature? What will happen to the solubility? It will also go down. Okay, so if we increase the temperature, the solubility will increase. If we decrease the temperature, the solubility will decrease for a solid dissolved in a liquid. So that one is pretty intuitive, I think. So the next one is a little bit less intuitive, so let's go over that. So what if we have a gas? A gas dissolved in a liquid. Okay. So let's think about, we'll think about temperature, and we'll think about pressure here. And we'll think about what happens to the solubility. So this one is opposite for a gas. Gases dissolve better in cold liquids. So if our temperature increases, then the solubility of a gas will decrease. Okay. If you decrease the temperature, then you'll increase the solubility. And this is why it's so important for, have you heard of them talking about like the ocean temperatures rising? Well, why does that matter? Well, if our temperature of the ocean increases too much, then there won't be very much dissolved oxygen for the organisms that are living in the ocean. So even if the temperature increases a little bit, that decreases the oxygen solubility a lot, or other dissolved gases that the things that live in the ocean. Okay. Or if we decrease the temperature, then we're increasing the solubility of gases. Okay. Pressure also affects the solubility of gases. So think about a pop can. What happens when you open a pop can or a bottle of pop? It releases the gas. Yes. Cool. So to put the gas in the bottle, they have to pressurize the bottle. So have you ever felt the bottle before you open it, and then you open it and then close it, and then it's like you can squish the bottle? Okay. So if you increase the pressure, the solubility of a gas increases. So this, if you think about your experience with pop bottles, that makes the most sense here. But I think that's the thing that we've experienced the most. If we decrease the pressure, then the solubility of a gas in a dissolved liquid decreases. So just like if you open the bottle, you're releasing the pressure, the gas can come out of the liquid. Okay. So these are the principles that we need to know to be able to do this topic. Questions so far? Okay. All right. Let's go to our topic. All right. It says, a student sees tiny bubbles clinging to the inside of an unopened plastic bottle full of carbonated soft drink. The student squeezes the bottle. So first, what's happening to the pressure in the bottle if you're squeezing the bottle? You're increasing the pressure. So what happens to a gas if you increase the pressure? Is it more soluble or less soluble? More soluble. So if you make the gas more soluble, then it will dissolve. You won't see those bubbles anymore. So the bubbles will go away because you're increasing the solubility by putting more pressure on the bottle. Okay, does that make sense? Okay, this one is a tricky one, so I just practice a lot of these. Okay, this one's long. So we're making rock candy. You know what that is? Rock candy is like the candy on a stick, like the sugar crystals on the stick. And you're making that, you dissolve the rock candy in water, and then you're gonna crystallize it. A student wants to make 2 batches. He finds an unopened box of cane sugar in the pantry. He starts batch A by dissolving sugar in 500 milliliters of hot water. He keeps adding sugar until no more sugar dissolves in the hot water. He cools the solution to room temperature. He prepares batch B by dissolving sugar in 500 milliliters of water at room temperature. So we have batch A, he's heated batch A. He hasn't heated batch B. Which one will be able to dissolve more solid? Batch A. Batch A will have more dissolved than batch B because if we heat up a liquid, it will dissolve more solid. Okay. Then it says, so then he lets them sit at room temperature, and what do we find? Well, we're probably going to get more candy out of the first batch because we were able to dissolve more to begin with. So more likely that rock candy will be formed in batch A. Okay. I have not seen one that says I need more information. So just kind of ignore that one and figure out from the top 3. Okay, let's do a few more of these because they're all a little bit different. All right. One of these is tricky. I can't remember. There's one that's the salt mine that's tricky, so we got to read them carefully. A pair of 100 milliliter samples of water are taken from a well, bored into a large underground salt deposit. Sample 1 is from the top of the well and is initially at 32 degrees Celsius. So that's kind of cold. Sample 2 is from it's Celsius. No, it's not that cold. Sample 2 is from a depth of 50 meters and is initially at 42. So this one, sample 2 is warm. Both samples are allowed to come to room temperature. So they go down. Both samples are going down. Okay. So if they both start at a warmer temperature and they both go down, but one of them was at a warmer temperature, what do we expect? Okay, so do we expect sample 2 to have a precipitate? They're both cooling down, but one cools down more than the other. The first one has a precipitate. This one cooled down more, so because it was initially warmer, more salt could dissolve. So we're going to expect more sample in sample 2 because it cooled down more. It was at a higher temperature, more salt could dissolve, and then they came to the same temperature. So I'm expecting a larger sample of salt from sample 2 in this example. Yes. Yes. Okay, next question. A student sees tiny bubbles clinging to the inside of an unopened plastic bottle. The student opens the bottle and hears a loud hiss as gas under pressure escapes. So what's going to happen if you release the pressure from the bottle? Are you making the gas more? Yes, you'll see more bubbles because you're making the gas less soluble by releasing the pressure. First, the bottle was under pressure. Then you were saying you opened it. Now there's less pressure. The gas is not soluble anymore because there's no pressure holding it in the liquid. Does that make sense? Okay. Yeah, this one's just like you got to practice a lot of these different versions. Okay, let's see. Is this the same one that we had? Oh, yes, it is. More practice. Okay, so same thing. We have salt from a mine. We dug a hole and we found some salt. Initially, one was at 42 degrees Celsius, and the other one is at 8. So we initially you pull them out and they're clear. Okay, this one's tricky. One of the samples drops in temperature. One goes from 42 to 20. The other one goes from 8 to 20. So it's increasing in temperature. So the second sample is actually going to become more soluble because it increased in temperature. Okay? So it says a sodium precipitate is formed in sample 1. What do you expect from sample 2? If it's increasing, it didn't have a precipitate, and now it's increasing in temperature.
No precipitate.
Yes, I agree with you. No precipitate because it didn't have a precipitate, then it increased in temperature. The second one, if it increases in temperature, that's going to make it more soluble. So you would not expect a precipitate to form. So I think that's the trick version of this question. Okay, the rock candy question again. Is this the same one? Do we have to go through it? So hot water versus room temperature. We expect more in the hot water, or we would expect a sample. Okay. Did we get the same version? Okay. All right, so we've gone through those. So make sure you've gone through practice. Make sure you understand all of the versions. Okay, great. Good. Next topic is calculating mass concentration. So we just briefly mentioned concentration in our lab discussion. So let's use that. So this problem, what I do is I always look at my units first, okay? So all I have to do is grams divided by liters for this problem. Okay, this one's nice. this is the easy version. They give us grams. They give us milliliters. So we just have to convert milliliters to liters and then do grams divided by liters and type that in the box. Does that make sense? And make sure we have the right sig figs. So this one is going to ask us a concentration. You just have to figure out what units to use by looking at the box. So this one would have, I'm going to divide by 1,000 to get milliliters. It just wants grams. We have grams, 9.598 divided by 0.5. I have 3 sig figs in my volume, so I'm going to keep 3 sig figs. The other one has 4, but we go by least sig figs when we're dividing. So 19.2. Okay, there gets to be some kind of tricky ones of the units. So let's find another one. Okay, deciliter. So it's looking for grams per deciliter. All right, we have grams, so that's pretty straightforward. We have to convert milliliters to deciliters. So this is hard for me. So I like to convert everything to liters and then go to the other one. If you can do it a different way, then you should do it the way that makes the most sense for you. But this is confusing for me. All right, so I know there are 1,000 milliliters in 1 liter. I also know that there's 10 deciliters for 1 liter. So that's going to help me figure out what I'm doing. All right, well, I have 50 milliliters. That's the same as 0.05 liters. Okay, and then, well, to go from liters to deciliters, I had to move my decimal 1, 2 to the, or just one to the right. So that will give me 0.5 deciliters. So then I just have to calculate grams per deciliter. And I know that because they told me in the equation, but if you look in your box, they're asking for grams per deciliter. So let's find our Alex calculator. Oh, I can type this in on my calculator. Okay, let's see if we got the right answer. And let's see, this has 3, this has 2, so I can only keep 2 sig figs. And then it's 170. I'm going to round to 2 decimal places, but this is not going to be acceptable for Alex. So I'm going to have to move my decimal 1, 2 times 10 to the 2.
Get the deciliters from milliliters, you times by 10? Or do you
I have to do 2 steps because it doesn't make sense to me.
Okay.
So I went from milliliters to liters. I divide by 1,000, and then I times by 10.
Oh, okay.
So I guess it would be like times by 100. Is that right? Yeah. Okay, let's see. I need to go back here, get rid of my, well, also let's make sure that we got it right. Okay. So I had to put it in scientific notation because of my sig figs. All right. I know there's at least one more that's more tricky than this, so let's see if we can find it. Deciliters. We already did deciliters. We're going to skip this one. I think there's microliters. Okay, that one's easy. Grams per milliliter. Has anyone got a microliters yet? Okay, maybe there isn't one. Okay, maybe it doesn't come up. Sometimes I remember this one having microliters, but maybe it's a different problem. So just make sure you're familiar moving through all the types of units that show up. Okay, questions on this one? This one's just like calculating grams per liter depending on the units. Okay, the next one is calculating molarity. Let's see if we can get through at least one of these. Calculating molarity using solute moles. maybe this is the one. Units. Calculating molarity using solute moles. Okay, this one has weird units. All right, so in general, we talked a little bit, this is the one that we talked about in the lab, about the lab. So concentration is measured using molarity, concentration. So concentration is always, not always, we use this capital M for molarity. Capital M is always moles per liter. On this particular question, you need to check. Sometimes they want the concentration, but they want it in different units. Okay? Big M is always moles per liter, but sometimes we need different units. So this one is asking for moles per liter, but they're giving us micromoles and they're giving us milliliter. So what we're going to do is we're going to convert both of those to the correct unit. So because my box is saying moles per liter, I need to convert the first number to moles. So I have 0.425 micromoles. Does anyone remember what this mu means? Times 10 to the minus 6. Yes, minus 6, yep. So 0.425 times 10 to the minus 6 moles. And if you want to remember those numbers, make this a little bit bigger till our boxes pop up. If we go to the data and let it load, if we go to SI prefixes, it tells us, it tells us what those are. So micro is this little u, mu. Micro is times 10 to the 6. So instead of putting mu, I'm just going to write times 10 to the minus 6. So that's the number that's going to go on the top. And then we need liters. We have 500 milliliters. We could do the same thing. 500 times 10 to the minus 3. Or, that one's easy for me to do in my head. I'm just going to move the decimal 3 times to the left. 1, 2, 3. So now it's in moles per liter. And I just plug that into my Alex calculator. So, let's see. We've got 0.425 times 10 to the minus 6. And then I'm going to, someone should like this, divide by 0.5 liters. And this will be my number. Oh, but it's like really small, so let's go to scientific notation. And then we have to decide how many sig figs. So this one has 3, this one also has 3, so we're going to keep 3. Well, there's only 2, so I'm going to add a 0 at the end. And I can also copy paste this. I'm just going to pick this up and put it in this box and put a 0 here. So 1, 2, 3 sig figs times 10 to the minus 7 moles per liter. Let's see if we got that right. Okay. Questions on that one? So that one's just like figuring out what units they want, figure out what units they give you, and convert and then divide. So let's do one more. I always use this box to tell me what's going on. So this is millimoles per liter, but they gave us micromoles and milliliters. So this question we have to figure out. So millimoles is going to go on the top. And they give us micromoles, so 0.0. There's a few ways to do this. So if you find a better way that works for you, you can do it that way. I'm going to change this to times 10 to the minus 6 because that's micromoles. Okay, and then I'm going to convert micromoles to millimoles, or moles to millimoles, because now I have this is moles. So for 1 mole, it's 10 times 10 to the times 10 to the minus 3 millimoles. Is this right? I feel like something's wrong. For 1 mole, oh, you're right. It needs to be for 1,000 millimoles. So it'd be like this. 1,000 millimoles is 1 mole. So this would be on the bottom. Or 1,000. There you go. 1,000 millimoles is 1 mole. And I can remember that, or I can look at this number. Okay. So this is, we've now converted this number to millimoles, and that's what's going to go on the top. And then we'll put 0.1 liters on the bottom. So let's type this in. 0.1233 divided by, oh, let's see, times by. Will it let me leave that? It's times. Times by 1,000 to get 2 millimoles. Oops, I need this micro. This needs to be times 10 to the minus 6. Oops. Times 10 to the, So this is 0.003 micromoles times 1,000 gives me millimoles. Then I'm going to divide this by my liters. I'm going to convert milliliters to liters in my head. So that's liters. And we get this number, which is really small. So I'm just going to push the scientific notation button. And then this one has 2 significant digits. It has 3 with a 0 after it. So that's 2. That one has 3. So I'm going to keep 2. So I'm going to copy my number. And put a decimal place after, or a 0, 3.0. So now I have 2 sig figs and my answer. So that is my answer. Okay, questions on that? So you just have to figure